This session is for OCR FP1. The topic is series and we're looking at June 2010 question 8. So the question says, in part 1, show that the fraction 1 over root r plus 2 plus root r is the same as, equivalent to, the square root of r plus 2 minus the square root of r over 2. And then in part 2 it says, hence, find an expression in terms of n for the sum of the series from 1 to n of 1 over the square root of r plus 2 plus the square root of r. So notice that this is the same as part 1. So having established an equivalent expression in part 1, then we're going to want to use it in part 2. And then in part 3 it says, state, giving a brief reason, whether the series from 1 to infinity converges. So let's have a look at part 1. So as I say, we have this fraction here, and the important thing is that the denominator of the fraction is irrational. And so we're going to treat it just as we would in surds. We're going to rationalise the denominator. So let's just have a go at doing that. So we'll have 1 over the square root of r plus 2 plus the square root of r, and all we're going to do is say that that is the same as multiplying the top and bottom line by root r plus 2 minus root r. So that is a similar sort of technique to what you've done when you've done some work on surds. And so the top line is just a 1, so we're multiplying that by root r plus 2 minus the square root of r. So all we now want to just make sure, we suspect that we should have a 2 here, and just let's make sure that we can see that that is going to happen. So you'll have a square root of r times the square root of r plus 2. So that's just going to be root r plus 2 times root r plus 2 is just r plus 2. Then you're going to have a square root of r times a minus the square root of r, which is just minus r, and just notice, of course, that these two terms, of course, are going to cancel out, aren't they? Which is what happens when we're rationalising the denominator. So we're happy enough with the numerator, that is in the form that we want it, and so we end up with the required result. So in terms of marks, you're really just going to get a method mark for rationalising the denominator there at this point here. So just making sure that method is clear, and then an accuracy mark for getting the right thing and showing it. So let's have a look then and move on to the second part, which is a few more marks for that. The important thing, as I say, it does say hence find an expression, so you are going to use this result that we've just obtained in part 1. So we're going to express this sum in terms of differences. And the way in which you want to do this is to set it out as neatly as you can in the form of a table, just looking at the first few terms. So we're going to start at r equals 1 and find the two terms, the differences. And then we'll look at r equals 2 and r equals 3, and we may even have to go to the next term. So when r is equal to 1, we'll have root r plus 2, so that will be root 3 over 2, minus root r, which is root 1 over 2. And then when r equals 2, we'll have root 4 over 2 minus root 2 over 2. And I'm not going to bother worrying about the fact that some of those fractions can be simplified, because it really won't be important, as we'll see in a minute. And then when r equals 3, we'll have root 5 over 2, and then the other term will be minus root 3 over 2. Now I will just find one more term, but you should at this stage just notice that some of the terms are going to cancel out. So we can see that there's a root 3 over 2 there, and a minus root 3 over 2 there, root 4 over 2 and a minus root 4 over 2. So this is the sort of thing that we should be looking for when we're using the method of differences. But I am going to just skip on and have a little look at what happens towards the end of the series. So let's just take the last two terms. So if r is equal to n minus 1, then r plus 2 would be n plus 1 over 2, and root r would be root n minus 1 over 2. And then the last term, when r equals n, would be the square root of n plus 2 over 2 minus the square root of n over 2. And now we have those terms in as well, we should be able to just have a little look and see if we can simplify things. So as I say, that term will cancel out with that term, and the root 4 over 2 and the minus root 4 over 2. So we can assume that this sort of pattern is going to develop all the way through. Similarly, these terms will cancel out with those ones, and maybe that term would cancel out with that one, and so on. So what we're left with is we've got two terms up here, and we've got two terms down here. And these are the terms that are now going to give us our sum. So if I just go back to blue again, then our sum, remember we're going from r equals 1 to n of 1 over the square root of r plus 2 plus root r. Then that sum will be, well, we'll have a minus, root 1 is just 1, so that's minus 1 over 2, and we'll minus root 2 over 2 up there, and then down here we'll have a plus root n plus 1 over 2 and a root n plus 2 over 2. And we could probably make that just look a little bit tidier. Take out a common factor of a half, and I'll put the positive terms at the beginning, so we'll have a root n plus 2 and a root n plus 1 minus root 2 minus 1. So we now have a sum for our series, and if we just check the marks for that part, there is a method mark for expressing it as the sum of differences. You also get a method mark for at least 3 terms at the beginning, and an accuracy mark for those 3 correct. The first 3 correct. And then the same sort of thing happens towards the end. You get another accuracy mark for the last 2. And you get a method mark for showing your cancelling. So I'm just writing those down so you can see where the marks actually come from, and then you have an accuracy mark here at the end for getting the correct sum. So 6 marks for that part. If we just have a look at the next part, the last part, then in part 2 we have this sum, and what we're asked to do in this case now is to consider what happens for the sum to infinity. So that means everywhere we would have an n, we would be replacing it by infinity. So hopefully you can see that as n tends to infinity, this term and this term are going to diverge. So as n tends to infinity, the root n plus 2 and the root n plus 1 will both diverge. They'll get bigger and bigger and bigger. So they will diverge. So in that particular case, it will not converge. So the series does not converge. And really you get 1 mark here for just a sort of sensible statement to show that it will not converge. But the important thing is, as I say, is the fact that these two terms will get bigger and bigger. So there is only 1 mark there. So don't forget, if you want to watch further revision videos, then you can go to the Further Maths website and follow the link.